Okay, hello everyone. Welcome to ASAP Seminar Episode 7. Today we have Zhixuan from Miller and the University of Montreal to present Forgetting Transformers, softmax attention with a forget gate. In this talk, Zhixuan will present his recent proposed forgetting attention mechanism and the forgetting transformer, which is called FOX, in which he introduced a simple way to incorporate a forget gate into softmax attention. He will demonstrate several advantages of FOX, such as not requiring rope. This is a totally rope-free position encoding mechanism. And this mechanism is also fully compatible with flash attention, allowing for very hardware efficient training. He will also show that Fox retains the known context and capacities of transformers, although it has like forget gate, but it has better long sequence modeling abilities. So let's very welcome Zhixuan to present his very interesting work.
Okay, thank you, Sunny, for the introduction. So let's get started. So the title is Forgetting Transformer, Softmax Attention with a Forget Gate. So this is joint work with Evgeny, Owen, and Aaron from Mila and UDM and Maker AI. So our code is publicly available. We have a very simple to use Triton kernel, so you can try this after this talk if you are interested. So first an overview of this talk. So first I will talk about the motivation, including why I think forget gates are useful even in transformers. And then introduce the method forgetting attention and the corresponding model forgetting transformer or FOX. And then I talk about how you can implement these things in flash attention and some practical considerations when implementing this bin. And then some results and analysis, we have some very interesting results to show you. And then talk about some future directions, including how you can like save computation based on the forget gate values. So motivation. So this is the original motivation. Like we know that forget gates are everywhere in recurrent sequence models. Many modern recurrent sequence models, there are some variants of linear attention. So there's a lot, and the list goes on. And we also know that forget gates are crucial for performance, and this has been verified many times. In these papers, you can read them. And finally, softmax attention and linear attention, they are closely connected. They're very similar in form mathematically. Actually, you can see softmax attention as a kind of a linear attention with an infinite dimensional state. In particular, this thing can be written in this dot product form. Okay, so yeah. So it's a very natural idea. So let's just try adding a forget gate to softmax attention. Sorry, let's try. Yeah, anyways. So next is why are forget gates useful? Even in transformer, which has a basically infinite memory. And the reason why I think it's useful is every model has limited modeling capabilities. For recurrent sequence models, it's limited by the number of parameters and also by the state size. And for transformers, it's mainly limited by the number of parameters because it has a memory that grows linearly with the sequence length, but it still has a limited modeling capabilities. And forgetting just allows you to just make things easier to model, because if you forget things, then you have less things to process. But I'll emphasize this point frequently in this talk, that modern models, they have many heads. Okay, so what you typically see is you have some heads that forget very quickly, but some heads that do not forget at all. Okay, so this is the motivation, and then let's about method. And start with some simple intuition. So forget gates is what this is really doing is essentially data dependent decay of input output dependencies. And so for example, let's consider this minimal recurrent neural network that maps an input sequence X to an output sequence O. And this is the minimum RN. You have this hidden state, and what you do is you have a forget gate. It's a scalar for convenience. That just decays your hidden state. And each time step, you add your input to your decayed hidden state. And for the output, you just directly use your hidden state. So like probably the simplest RNN you can have with a forget gate. So you can expand this recursion. Just expand this recursion, and you can easily show that you can write each output OI as a linear combination of your input Xj with coefficient Fij. And this Fij is just the product of forget values between your input and output. So output is I and input is j. So this is the index is from j plus 1 to I. And this should be pretty obvious because this bin is multiplicative. So if you expand this bin, then you get a product of forget values. Okay. Anyway, the takeaway here is just you don't need recurrence in order to have a forget gate. And transformers do not have an explicit recurrent form, but yeah, of course we can add a forget gate. All we need is just to add this Fij factor. And this is called, we call this the forgetting attention. So as usual, you have this QKV projections. But then in addition to that, you also have a forget gate. And here the input is X. So this is basically a linear layer and then sigmoid, and it's a scalar. This is very important. You can get rid of the bias in some small scale experiments. This doesn't matter. So, but it might be useful in some other cases. So that's why we keep the bias here. And then you compute this Fij factor as usual as the product of forget values between J and I. And then the attention, okay, all you need to modify here is just add this Fij factor to your softmax attention. Okay, that's pretty much the method. There's nothing fancier than that. But you have an exponential, then it's a very natural idea to move this multiplicative factor into the exponential by taking the log. So here Dij is just the log of Fij, and then you can move it inside the exponential. And this has many benefits, including it's numerically stable and much easier to implement, as you will see later. And you can also write this elegantly in a matrix form. So you can just organize all the Fij factor into a matrix, and then you take the log as before, you get this D matrix, and with entries Dij in it. And then you can write the whole thing in this form. So it's just the familiar matrix formulation of softmax attention. And yeah, you can see this as a decay matrix. But yeah, that's pretty much the method. Any questions so far? I think it should be pretty straightforward. Okay, if not, then I will move on. Yeah. Some comments. So here we don't we don't use we don't show the scaling factor here. Typically, there's a square root of d, and in practice, we always have that. So just a small note. And also, if you have a multiple heads, then we will have one forget gate per head. Okay, so and each of them will have their own parameters. And this is very important. In some experiments, if I share a single forget gate across heads, then it performs poorly. So don't do that. And also, as I mentioned, this forget gate is a scalar, it's not a vector. So the additional computation and parameters introduced are basically negligible. Okay, it's very cheap. And there's no need, in my experiment, I find that there's no need to use rope. So this has several benefits. It's very convenient for long context fine tuning because you don't need to adjust data, for example, in YARN. And also it's convenient to add to non-standard attention mechanism like multi-layer attention or native sparse attention. You've worked with this method, you will know that adding rope to these methods is pretty awkward and it's elegant. And it's also hyperparameter free. This is unlike rope or alibi, where you need to adjust the hyperparameter based on the context length. So yeah. So now I'm going to talk about connections to prior and concurrent work. So first, I'm going to talk about connections to linear attention models with forget gates and, for example, GLA and Mamba2 and many more. And also connection to alibi. And many of you would probably interested in the connection to steep breaking attention, which was a previous talk in this seminar. So I'll talk about that as well. But let's start with the linear attention thing.
Sorry to interrupt. We have a question in the chatting room. So Econ has a question. What if all FT is small? Does the forgetting mechanism still function correctly?
So in practice, you see that some heads have a very low F, but for some heads it's extremely close to one, always close to one. So it's learnable. So that's not a concern really. Yeah. So my point is that if there is a long-term dependency in the data, then the model can learn to learn F less close to one. Does that answer your question, Ika? Okay. Thanks.
We have another question.
Yeah.
Have you explored using constraint to balance the FT values?
No, but I have tried some other parameterizations for F. So here I'm just using a simple sigmoid and linear layer, but there are some other tricks you can use. You can look at how Mamba did this, and in GLA they also have a temperature hyperparameter, and that's meant to encourage the model to learn long-term dependency. I've tried all of them. They don't make any difference in my case. I don't know why. Yeah. There's another question. Have you tried long context continual training experiment to show that you can really extend it through fine tuning? Not yet, not yet. But this is a future direction that I will talk about later. Yeah. But the short answer is I think it's gonna work. I don't see why it wouldn't work very well. Yeah. Well, that's unclear, but I don't think there'll be a problem. I know you are talking about vanishing gradient of sigmoid, but Um, in practice, I find that forget gates tend to learn pretty fast. Yeah. But anyway, this needs to be experimentally verified. So we'll see. Yeah. Um, okay, I see there's no further questions, so let's move on. I'm not going to assume everyone here is familiar with linear tension, so here's a quick introduction. So what you do in linear tension, you just replace the exponential QK thingy with this dot product. And phi here is some feature representation, but it could be pretty simple. You could just use some element-wise activation here. And the nice thing about this is it allows you to reorder the computation, and you can write the whole thing in this recurrent form. And what you do here is you are accumulating the outer product between your values and keys, and you also need to account for the denominator. So you also have a term that's accumulating your key. And then if you need the output, you just do a matrix vector multiplication between your matrix value memory and the query. And you do the same for your denominator. See here. So the nice thing is that you now have something similar to a recurrent neural network. You have something like a hidden state input. So it's very natural to add a forget gate in front of your hidden state. And it turns out that you can go back to this parallel form of linear attention. And the result is just this F-edge factor, as we see before. So this is shown in GLA number 2, even though it's not exactly like this, but the idea is pretty similar. Yeah. So now all you need to do to obtain softmax attention with forget gate is you just change this dot product thingy back to this exponential q dot product k, and that's pretty much. And this is the original motivation. This is actually how I came up with this idea. Yeah.
Yeah, so you are
Yeah.
essentially
Mhm.
changing from linear attention back to softmax attention, but
Yeah.
incorporating those techniques developed in the linear attention literature, right?
Yeah. Yeah. You can think of it that way.
And also relevant question, do you think it makes sense to put the cumulative product term inside of the softmax operator?
Yeah, I don't think that makes sense. Um, for for particle point of view, if you move this thing inside, what will happen for distant uh, for so if J is for distant dependency, what happens is that this will be 0, and if you take the exponential, this whole thing will be 1, and that is really weird. Doesn't make sense at all to me. And from aesthetic point of view, if you view this if you view softmax attention as a form of a linear attention but with an infinite dimensional space, this is just a very natural thing to do, right? Because in this case, you can just think of this as a mapping to infinite dimensional space, and you can write it in a recurrent form. Then the only thing that makes sense is to add a forget gate here. So yeah, that's just my thoughts. I guess you've done some experiments and you find it doesn't really work well, right?
Yes.
Yeah, that's the most important aspect. Yeah.
And I have another question. So in this case, the reason why this Fij term could be extracted outside the dot product is because it's a scalar valued
Mhm.
decay term. And so in member 2, we know that this term could be extracted outside of this dot product, so you can separate the dot product from this forgetting term, right? But what if the forgetting this decay term is a vector valued, and in the GLA case, we show that we need to multiply the query and the key by this forgetting factor before doing the dot product. And what is like the corresponding forgetting transformers with data dependent fine grained decay? I'm very curious about it.
Short answer is there's no corresponding version of practical corresponding versions of like vector value decayed. Um, there's just no way to do that. The only way to do that is again to use this recurrent view of linear tension view of softmax rotation and treat this as an infinite dimensional a mapping to an infinite dimensional space. In this case, because this your hidden state is infinite dimensional, your vector valued Fourier gate also has to be infinite dimensional. I don't know if you can use some clever trick to achieve that, to achieve equivalent of infinite dimensional Fourier gate, but I don't know whether that's possible at the moment. Yeah.
Yeah, that makes sense.
Yeah.
So by using this exponential kernel function, the forget gate would also need to be like in infinite dimension.
Yeah. Yeah. Yes.
We
Okay.
have another question in the chatting
Mm.
room. So is it possible to rewrite forgetting transformers in a additive bias similar to alibi?
Yeah, that's in the next slide. Yeah. Okay. So recall this logic bias form. Again, this Dij is the log of Fij, and which is essentially the sum of the log of your forget gate between your keys and queries. So you can show that if you use a fixed forget gate like this, this is M is a hyperparameter, then you can show that this Dij is just minus M and J minus I. So J minus I is just the distance between your keys and queries. So, and those familiar with alibi will recognize that this is just alibi. So what that means is forgetting attention can be seen as a learnable and the data-dependent version of the alibi. And, and also, of course, alibi can be seen as a fixed and data-independent version of forgetting attention. The natural consequences of this is, okay, so forgetting attention is strictly more expressive than alibi. Of course, it works better in practice, and we will see that later in the experiment part. Yeah.
I would imagine this is especially useful in a non-context modeling because alibi is like a data independent decay term.
Yeah.
So no matter of the content, it will always do such decay. And I think main critics of alibi is that it does not have a very good non-context modeling ability comparing to rope because it forgets too quickly. And since you are using a data-dependent decay term, so the model can learn to not forget, and this is very useful. This is like the key benefit of like data-dependent decay.
Yeah. So actually in the experiment later, you'll see that being learnable is probably more important. So you can have a learnable but data independent forget gate. It will also have decent performance, but still being data dependent is still better. But if it is fixed like alibi, then the performance is just terrible. Yeah.
Yeah, and we have another question from the chatting room. For alibi, does it has different the decaying speed for different head?
Yes. Yes. Yeah. So I should add the subscript H here and add a superscript H here. But yeah, it has different different decay rate for different heads. Yeah.
So maybe for some heads it decays in a quickly manner, and for some heads it decays very slow. It's
Yeah.
very similar to Redlet, right? Because in Redlet, they also have like data independent decay, and they have different forgetting speed for different head. And in
Yeah.
this sense, the number of head serves as like a to make a fine grained control over the decaying speed for different head.
Yeah. Yeah. In alibi, they just have different. In the original alibi paper, they just have different decay rate for different heads as well. Yeah. Okay. So now steep breaking attention. Um, so quick introduction to steep breaking attention. So you have a QK dot product. And here the interesting part is to take the sigmoid. And then you do this steep breaking process to get a weight for each query and key. So I is index for query and J is index for key. And then you just write each output as a linear combination of your value. So that's the method. The similarity, of course, both have a data-dependent decay. So difference. Okay, so this is what I think the key difference is that in steep breaking attention, the retrieval aspect of the attention and also decay aspect of the attention that is coupled. So this beta is responsible for both. So, and for those of you familiar with sequence modeling, this part is a way more important because this is what replaces softmax. If you don't have this, nothing is gonna work. But if you don't have this, it still works, but probably not great. And so in forgetting attention, softmax is responsible for the retrieval part, and for the forget gate is responsible for decay. So in our case, it's different. So I'm not saying which one is better because it's steep breaking attention is clearly there's a reason why they design it like this. It's used to implement the first match inductive bias. And also the SPA decay is query dependent, but in our case, it's not query dependent. It only depends on input. Again, SPA decay is meant for implementing first match, and instead of like, so if you have a forget gate, you can imagine it's more like we want to do retrieval within a local scope. But this is not saying that SBA cannot do that. It can certainly do that. It's just different motivations. Yeah. So and finally, you don't have to see these two things, see them as competitive methods, like different methods. You can certainly combine them. All you need to do is just add a you just need to add a Fij factor here. It may be redundant, but we don't really know that. Yeah. Okay. So now let's talk about how we can implement this being efficiently using flash attention. So first, there's a simple trick for computing this Dij efficiently. So first, you just compute the cumulative sum of the log of your forget gate. So just notice that here the index starts from 1. Okay, here it starts from 3. So here is 1. And for example, C1 is just a log forget what log F1, and C2 is log F1 plus log F2, and so on and so on. And then you can easily show that Dij is just Ci minus Cj. And this is very simple to implement in practice. Just a graphical, just an illustration of how this works. For example, if your C has 5 elements, and this is the D matrix that you want to compute. And then each entry of Dij is just the corresponding Ci minus the corresponding Cj. Okay, so you just need to transpose it, and then you do proper broadcasting. You just subtract this bin from this bin, then you can get your D matrix. And those familiar with flash attention should already be able to imagine how you can implement this in flash attention. It's really simple. So this is just a flash attention, the basic idea. So you split your queries and keys into blocks, and then you do across the query dimension, you do things in parallel in different thread blocks or SMs. And then across the value or key dimension, you scan the block sequentially. And what you do in each of this what you do in each of this thread block is you are accumulating the partial output. So here you're accumulating the numerator part, and then you also need to accumulate the denominator part. So all you need to do to add add a forget gate to here is just you need to compute the corresponding block of Dij, and for that you need to load the corresponding blocks of Ci and Cj. And you compute it, and then you add it to your attention logic, and that's pretty much it. So here I'm ignoring the numerical stability thing, but that's just a trivial to handle. Yeah. There's just one potential issue with this global Q-sign implementation, which is this thing called cancellation error. For example, because of every floating point number has a finite position, you get this weird effect that A plus B plus C minus A plus B is not equal to C. And this is very problematic. Could be problematic if the sequence is very long. And here, this is what we did, what we do here, right? So we just compute the cumulative sum, and then we subtract subtract two very large numbers to get Dij. So that could be problematic. So it's very obvious that you will get this cancellation error when computing Dij, but it turns out that you also get this cancellation error during the backward pass when you are computing a gradient for the log of your forget gate. This is not super obvious, but you can do the math and you will show that there will be cancellation error here. So I spent a little time to think about this. It doesn't seem possible to avoid both in the backward pass. You could avoid the cancellation error for Dij in the forward pass, but it doesn't seem possible to do that in the backward pass. In my experiments, I just use the global Q-sign implementation because it's very easy to implement. But and I use FP32 for the computation of all these means, and it's totally fine for context than 32K. But just a caveat that it might be problematic for super long context. For example, if you use 10 million tokens, then this cancellation error might be significant. But in that case, I guess you can just use you can just use an even higher position to compute this thing. But in this slide, I just show how you can avoid the cancellation error when computing one of these. For example, this is how you avoid the cancellation for Dij, and this is how you avoid cancellation error for the gradient. But these are super technical, so I guess I will skip this. So if you're interested, you can check out these two slides later.
I was wondering, did you actually use this trick in implementation?
Which trick?
And this trick to avoid a cancellation
Oh,
error.
no.
Because I
No.
check out your code, you simply like do the difference
Yeah.
of creative sum.
Yeah. Because
I thought,
this is
yeah,
go
I thought
ahead.
it because like the cancellation error was also mentioned in the Mamba 2 blog post. And I was thinking, okay, they are using some fancy trick to avoid such cancellation error. But in the end, they also use the difference between the cumulative sum for actual implementation.
Oh, really? Okay.
Maybe people
Yeah,
just don't care about this
yeah,
cancellation
yeah,
error in
yeah.
practice.
Yeah, in practice, I don't see any issues with this. And I've also tried this trick, but I don't see any difference in performance. So, and this one is the QSAN implementation is super. This version is super easy to implement. So there's no reason why I would do something more complicated. Yeah. Mm. Yeah. So also if you're interested, if you have your own fresh attention implementation, and if you want to try adding a forget gate, this I recommend just doing it like this. It's very simple to do and very easy to debug. Unless you see some issues, I guess you don't need to bother with this more complex implementations. Yeah. Okay. And then a little bit of architecture design. So first thing, we don't use a rope by default. Then we test two different architectures. One is the standard llama architecture. And what we do is we just replace rope in the llama architecture with forget gates. And we call this Fox llama. And we also tried improve the pro architecture. It's basically Fox llama plus some components commonly used in recurrent sequence models. QK norm, output normalization, output gate, and data-dependent token shift for keys and values. So some of you might not be familiar with this, but what you do here is basically you are interpolating between your previous keys and your current keys. And this could be helpful for implementing induction heads. And some of you might know that short convolutions are frequently used in recurrent sequence models as well. And this is functionally, and this K-way shift and short convolution is functionally similar. By the way, I also tried adding it to query. It doesn't seem to help at all. So any architecture just look like this. So this is the usual attention part. We have QK norm, K-way shift, and then output gate and output normalization. Yeah. But in the experiment, we also test the standard transformer with the pro architecture. So it's absolutely a fair comparison. Okay. Let's move on to experiments. Yeah. So the core question we try to answer is, does it forget things? And the answer is no. What happens in practice, as you will see later, is that you have some heads, actually probably most of the heads, they forget very quickly. And this, you can see this as a local head. But then you will notice that some heads have extremely slow forgetting. And these are global heads. And these heads are probably responsible for the long context modeling part. So overall, you will see later that similar to the transformer, Fox is actually great at modeling long sequences. And perhaps a little bit counterintuitive is that the longer the sequence, the better Fox works. I will explain why later, but so this is an overview of the experiments that I'm going to talk about. First is a long context language modeling. And there's a analysis that I want to emphasize, which is per token loss analysis. This is a very interesting thing that I'll show you later. And then just a needle in a haystack just to test the long context retrieval abilities of the models, and then some downstream tasks and a bunch of analysis. For example, later we will see whether rope helps in Fox, and also we'll see data independent and fixed forget gates. So, so we compare, we use the following models for comparison. Fox Pro, Fox Llama, as mentioned before. And we also use a transformer with our Pro architecture and transformer with the standard Llama architecture. And we do find that because we use a very long training context length, we do find that it's important to adjust the theta in rope, to use a very large theta in rope. And then Mamba 2, Delta Net, HN2. And this is just to show the superior long context capabilities of transformers and also Fox over this linear complexity recurrent sequence models. For the data set, we use a long core 64. This is a pretty new data set, and it's basically a pre-tokenized long sequence subset of a rapid drama V2. So the reason I use this is because it's all long sequences, so it's very convenient for research purposes. But in hindsight, this is probably not a good idea because it has some really strange design choices, and it's not great for downstream tasks. But it's very convenient to use. So the largest model we train is only like 760 million parameters. Unfortunately, we just don't have that much resources to train larger models. And we use 48 billion tokens for training. So the context that we use a bit longer than usual is 16K training tokens for training. And for evaluation, we use much longer context length just to test the length extrapolation abilities of the model. And we also did a bit of a hyperparameter search. So for each model, we search the learning rate. For Fox and Transform, we also sweep the head dimension a little bit. Just some interesting facts about optimal hyperparameters. So I find that Fox typically prefers more heads than the transformer. So that's a bit interesting. I'm not exactly sure why this is the case, but this shouldn't matter for larger scales because the larger models typically have more heads instead of larger head dimensions. And I also find that Fox prefers higher learning rates than the transformer. And Pro architecture models prefer higher learning rates than the Llama architecture models. So what you see here is so the overall effect is just that you see Fox Pro, the optimal learning rate for Fox Pro is it's pretty high, but the optimal learning rate for Transformer Llama is pretty low, relatively low. So this is just to say that if you want the optimal performance, you probably need to tune the hyperparameter a little bit. But even if you don't tune the hyperparameters, which means you just directly replace rope with forget gates, it's still pretty good. So yeah. Okay. So now I'm going to introduce the main metric. This is a very important thing, per token loss. There's nothing fancy here. What we are doing is just we are reporting the loss at each token position. But just to be precise, what you do is you take a sequence, right? You pass it through the model, and you get the logits or the probabilities at each token position, right? And then you have your language modeling targets. Then you just calculate the loss at each position. And we call this Li. So you can plot this thing for different I, then you can get a curve. So these are some these are some typical patterns you will see later. So the x-axis here is the token index or the position in the context, and this is the loss, the value of the loss, and this will be the training context length. Okay, so in general, you'll see it's at least within the training context length is typically monotonically decreasing. And some of them will plateau after some token position. Okay. Any questions about the definition here? This is very important. Okay. Yeah. So the reason why I'm interested in this thing is because it reflects a model's long context modeling capabilities. So for a perfect model, Li should be monotonically decreasing with respect to I. And the reason is the later tokens are easier to predict. And that's because when predicting later tokens, you have a longer context. Yeah, so you have more information. And then the slope of a per token loss at a particular position will roughly correspond to the model's abilities to use tokens that are I steps earlier for its prediction. To see this, you just look at this example. So in the first example, we are predicting the 90th token, given a context of 90 tokens. And here we are predicting the 100th token given the previous 100th token. So difference in these two cases is that in this case, you have 10 more tokens. Yeah. So if this is lower than that, it means the model are actually using these 10 extra tokens for its prediction. But in some cases, you will see that they're pretty much the same. It just means that the model just probably just ignores this extra 10 tokens, either because it's not able to, or because it's fundamentally not useful, but that's typically another case. Okay. So it's very important to distinguish between this per token loss and perplexity. This is a very important point because many people make this mistake. I've seen this many times in different papers. So first, we have this per token loss, and then we also have this cumulative average of per token loss over context length. So yeah, so it's just for each L, you just take the average, and that's a cumulative average. And perplexity over context length L is just the exponential of this thing. So the reason why I mention this is because even if Li, the per token loss, it plateaus after some token position, the cumulative average and also the perplexity will still be monotonically decreasing. So this could be extremely misleading. So don't do that in the future. Now the results. There are several models. So first you can compare Fox and Transformer. So this is a Fox and this is a Transformer. Okay. This is Fox Pro, this is Transformer Pro, and this is Fox Llama. This is Transformer Llama, so it's just better. And also you can notice that for both Fox and Transformer, the per token loss is monotonically decreasing. But if you look at this recurrent sequence model, you can clearly see that their per token, for example, this one is Mamba2. You can clearly see that their per token loss start to flatten after maybe 4K. And they basically completely plateaus after 10K tokens. So what this means is just that this existing recurrent sequence models, they cannot really fully utilize their long context for prediction. And here I'm also showing the perplexity over different context length. As I mentioned before, the slope here could be extremely misleading. For example, here you see Mamba's per token loss basically plateaus after 10K, but if you look at perplexity over different validation context length, it will still be monotonically decreasing. And again, many papers make this mistake, and they use this to claim that their model's prediction improve with a longer context length. So I hope nobody in this talk will make this mistake ever again. So this result is just for so I see a question. Did you address computational costs? I'm guessing slightly more, but not dramatic. So if you're referring to the comparison between Fox and Mamba, and this is these two things, because we use a very long training context length, it's a significantly more expensive because it's quadratic complexity. But I've also tried using shorter training context length. It's still better. Okay. And then this is extrapolation result. So previously, I'm just showing you the left half of this plot, but now I'm also showing extrapolation. So this is a familiar transformer behavior. It just blows up beyond the training context length. And this is a Fox llama. So it goes out a little bit, but then it plateaus. And this is a transformer pro. For some reason, it's pretty decent extrapolation, and then Fox Pro model. And here it appears that it may appear that oh, sorry. The question regarding the computational costs is versus vanilla transformer. In terms of flops, it's basically the same. But because we implement the flash attention kernel in Triton, it's much smaller than the official CUDA implementation. But theoretically, if you optimize both perfectly, the throughput should be the same. Yeah. So yeah, in this part, it will appear that this recurrent sequence model such as Mamba and HGRN2 and DeltaNet, they have perfect extrapolation. But that's actually not the case. Yeah, so I'm going to skip this, but what I'm emphasizing here is just that if you want to understand the long context abilities of a model, you should look at the slope instead of the actual values of the loss. For example, here you can have a very big model with terrible long context capabilities, and its protocol loss will look like this. So overall, it's lower than that, but then it will plateau after central composition. But if you have a small model but with very good long context capabilities, it will be monotonically decreasing. And then in terms of extrapolation, this is true extrapolation because this means the model is actually using the actual context during in the extrapolation regime. But for this one, it simply means the model is ignoring the extra context that's out of distribution. So I like to call this a fake extrapolation, but this is a true extrapolation. And by the way, if you go back, you see that all models have pretty much a fake extrapolation. Except for here, maybe you can see goes out a little bit, but then it goes up. Yeah, so to get this kind of a protocol loss, you just need to train a sliding window attention model with a very small window size, and you're going to see this kind of pattern. And also, this protocol loss is pretty useful because you can see a qualitative difference between different models. And this is most obvious with small models. And if you use a very long training context length. So you don't need to run those expensive, you don't need to train a huge model and do a needle in a haystack test to understand the long context abilities of a model. So here it's a very small model, 100-ish million parameters. And although in order to see this kind of pattern, you are going to need real long sequences. You cannot just concatenate short sequences, and you are not going to get this plot. Yeah, so there's a question in the chat. So I'm interested in the training dynamics of per token loss. Did you plot Li on intermediate checkpoints? The answer is yes. I will show you later. Yeah, so regarding this point, so you cannot just concatenate short sequences, but this is for evaluation. I'm not sure whether you need this during training. So maybe you can just mix long and short sequences during training, and then during evaluation, you need to use long sequences, real long sequences in order to see this trend. And then just some visualization of this F matrix and also the attention matrix, which is the result of softmax. So I'm showing two different heads on different layers. So you can see some heads have this extremely strong decay or very quick forgetting. And accordingly, the attention just focuses on local entries. But for some heads, the decay is really weak and the attention scores are distributed across the entire context. And I should remind you that each entry of this F-edge matrix is a product of a many forget gate values. So for example, the entries at the lower left is like product of forget gate values, like 10K forget gate values between 0 and 1. So this is a really weak decay. Yeah. So what I'm trying to say here is just that it really can learn to not forget at all if necessary. And then needle in the haystack. So we use two different modes, and one is the standard mode. It's just the needle is just a fact. For example, the best thing to do in San Francisco is blah blah blah. And then this needle is hidden in a very long document. And then at the end of the document, you ask the model what is the best thing to do in San Francisco. And then there's a prefix. So I have to add this prefix, otherwise, because our models are pretty small and not instruction tuned. If you don't add this, it's going to be terrible. And there's also this easy mode, where we just have both in the needle, in this easy mode, the needle includes both the question and also the answer. So this is just a pure pattern matching. And it's easier for small models without instruction fine-tuning. So here, this is on the right, I'm showing the easy mode results, and on the left, I'm showing the standard mode results. Again, this is a training context time. So first thing you can notice is recurrent sequence models, they just are terrible at this task. And transformers and Fox, they are all pretty good within a training context length, except in this case. In these two cases, I guess the model is just too small and the standard mode is a bit too difficult. And you can also see Fox Pro and Fox Llama and Transform Pro have decent extrapolation in this task. So in particular, this is pretty strange. Transform Pro seems to be pretty good in this easy mode. So this is really strange considering its per token loss just basically blows up beyond the training context time. So I don't really know what's going on here. Yeah. But anyways, this just to show that folks can learn not to forget. And I mean, of course, I mean within the training context then. Okay. This is just a warning. I find that extrapolation behavior is really unreliable. So here what I'm showing you is a different number of training tokens. For example, this is 16 billion tokens and 48 billion tokens. And then different learning rate. And this is the easy mode needle in a haystack test. So you can see the performance really varies across the different hyperparameters. In general, what I find is that if you train longer, you have a worse extrapolation, as if it is overfitting to the training context then. And if you use and also smaller models plus longer training context length, you typically can get better extrapolation and vice versa. But I'm not exactly sure about learning rate because I don't have many data points. And this is what it looks like in terms of per token loss. So if you don't train very long, 16 billion tokens, then it's a very nice plateau. But if you train much longer, then you get this degrading per token loss pattern. And by the way, this is not different track points because in terms of learning rate schedule, I've also tried plotting different track points in a single training run. It's basically similar to this. But this is just for extrapolation. Within the training context length, there isn't much change. It's just a very nice monotonically decreasing curve. I don't see the behavior change too much within the training context length. Yeah, so the conclusion is extrapolation is nice, but this is really unreliable. So if you want a long context model, it's probably just do long context fine tuning. How many slides? Okay. And then short context downstream task on language model evaluation harness. There's nothing too interesting. You just need to know that Fox Pro is best one. And Fox Llama is also better than Transformer Llama. And then long context downstream tasks. So in general, Fox just has a similar performance as Transformer Pro, even though arguably you could say that Fox Pro is a bit better than Transformer Pro here. And Fox Llama is also a similar performance as Transformer Llama. And then all these models are much better than the recurrent sequence models. So there are some tasks where this is super obvious. For example, this track all softmax attention models are pretty good. And they are much better than recurrent sequence model. And also this gamma report test. I don't know what's going on here. Maybe, yeah, it's probably just that these tasks require a lot of long context understanding or things like that. Yeah. And now onto analysis. So I tried different model size. For example, this is a 300 million-ish parameter model, and this is 700 million-ish parameter model. And then with different training context length. So different colors represent different training context length. And then the solid line is Fox and dashed line is Transformer Pro. So you can see this clear trend that as we increase the training context length, the gap between Fox and the Transformer increases. But as we move to larger models, the gap becomes smaller. Okay. So this is pretty interesting. And I have this hypothesis that the benefits of forget gates actually depends on the ratio between model size and the training context length. And larger models because larger models can better model long context, and thus forgetting is less important. And seeing this part it's also very natural to ask, okay, how would the Fox work with even larger models? I don't really know. So I welcome everyone here to try this at larger scales. And then aberrations. Yeah, we basically just ablate everything, but just to highlight some points. First thing, you can trust me that everything in the Pro architecture, this QK node, output gate, output node, cable shift, they are useful. You can check the result later. I just want to highlight that if you remove both the forget gates and also rope, then it's terrible performance. The performance is terrible. So you need to have at least one of them. And then it's really unclear whether rope is still useful when you have a forget gate. For example, this is a Fox Llama plus group, and this is Fox Pro and Fox Pro plus group. So in this case, it improves the perplexity a little bit, but in this case, it's not useful at all. So, but it's certainly not necessary. So you might as well just not use rope in Fox, but you could do that if you want to. So the final experiment is we just also try data independent forget gate. So this is the standard data dependent forget gate with a linear layer. So to get the data independent forget gate, all you need to do is just remove this data dependent part. You only have this bias. And then we also have this fixed forget gate. As I mentioned before, this is equivalent to alibi. And by the way, this is just how you do learnable alibi. Okay. And so for these two data independent forget gates, I find it pretty important that you initialize this bias properly. Otherwise, it's not gonna work. But for this one, you can just initialize this to 0. It's totally fine. So the exact way I initialize this is where I use two hyperparameters, Tmin and Tmax, such that if you initialize the fixed forget gate with these two hyperparameters, it is basically equivalent to alibi with maximum slope 1 over Tmin and minimum slope 1 over Tmax. For example, the typical value in alibi is 2 and 256. Okay, results. So we always fix T minimum to 2, and then we vary T max for this for the data independent forget gate and the fixed forget gate. So these two are comparisons in the Dharma architecture, and these two are comparisons with the Pro architecture. And this is so data depth is just a data dependent forget gate, and fixed is a fixed forget gate, and then we have data independent forget gate. So in summary, it's just data dependent forget gate always works the best, and it's also hyperparameter free. So that's some interesting things here. Using a Llama architecture, if you tune, it seems that in this particular case, data independent forget gate is also pretty decent. But in the Pro architecture, the gap is pretty obvious. But if you use a fixed forget gate, which is just alibi, it's always terrible. Yeah, so just don't do that. Okay, now quickly go over the future direction. First thing, we need to try this at larger scales. I really don't know how it will scale. And make this bidirectional. And then it's a long context fine-tuning thing. I think it should be great. I haven't tried this personally. So first it's learnable and data dependent. So it should adapt quickly to the longer context. And also we see that it has a better length extrapolation. So in principle, during fine-tuning, it should be very stable and it should learn faster. And we can also try adding forget gates to pre-trained models such as Llama 3, and then fine-tune. And you should adapt quickly. And finally, this is the thing that I'm currently working on. Is you can save computation based on forget gate values. So what I observe is most heads in the model actually pretty local. Again, this is the F matrix. It looks like it's all black because only the diagonal entries are non-zero. So it appears that it's all black, but these are basically all local heads. Okay. And then this is a corresponding attention map. So what that means, if a head only uses a local context, there's really no need to waste compute on distant tokens. They don't affect the output anyways. So what you do in practice is as you know, this Dij factor is very easy to compute. It's just subtract a scalar for another scalar, you can compute Dij. So if you notice that Dij is very negative, you can just ignore the computation of this whole thing. And this can really save you a lot of computation, because for these local heads, you're just skipping most of the computation. So assume that these are all the heads in your model, then the saving could be like 80% or 90%. So I've tried this with a small model, but a very long training context length. It seems to work pretty well, 30% throughput improvement. And because the model has an MLP part and the attention part and some other components, so the actual amount of flops saved in the attention operation should be much larger than 30%. So I haven't measured that myself, but it's probably around 60% or 70%. So this is a pretty promising thing. Yeah, that's pretty much it for the talk and some references. Thank you. Yeah, any questions? The question, we have a question, how does the ratio of local heads, global heads vary across layers and model sizes? I don't have a definite, I don't have a answer yet. I'm going to do that very soon, probably today or tomorrow, because that's needed for the submission. But I cannot guarantee my answer is correct, but my impression is that lower layers and top layers, they typically have more. Yeah, I'm not sure my memory is correct, so I just not answer this question. Yeah. Oh, so the training dynamics of per token loss. Um, it's just this one. But as I said before, this is not intermediate checkpoint. But I also tried using intermediate checkpoint. For example, if in a 48 billion token run, I plot the per token loss of the intermediate result at 16 billion tokens. It's pretty much it's a similar pattern like this. So in general, the per token loss within the training context length, it doesn't change too much. But beyond the training context length, it typically gets worse. Yeah. The question, the fact that most heads are local is consistent with a lot of other work. It may be that some specific type of long context fine-tuning might be needed to see more global heads. I mean, if the model learns only a few global heads, and then it's still great at long context modeling, then that probably just means you only need one or two global heads in order to have this kind of a long context capability. I'm not sure whether you want to mess with the model to encourage it to have a more global heads. It's probably just not necessary. All right, thanks.
Oh, okay, maybe let me ask some question.
Okay.
So for extrapolation evaluation, you said that it has to be done in non-context data, otherwise you will not see this trend, right? So I was wondering, except for the long Chrome 64 benchmark, do you have like any other recommended data set that is more easy to use? Because for the non-Chrome data set is like pre-tokenized, and we cannot simply easily change the tokenized we're using. So I was wondering, like say, do you think like a book 3 would be a good test benchmark for it?
Yeah, in general, I think book data sets would be great for this purpose. Probably not for training though, because it's a very specific type of data set. And also I've seen some people use proof pile. I don't know what that is exactly, but maybe that will also be a good idea. Yeah.
Well, I think proof pile is a like a archive data set.
Okay.
They have like many mathematical archive paper from archive, and then they tested. It's very known and it's full of mathematical equations.
Okay. Yeah. I'm not sure because you see that the what I use is pretty long, like 64K. I'm not sure archive hoops will be this long. Yeah. Yeah. And also you said you I'm not just referring to extrapolation. Just within the training context that you, of course, you also need real long sequences. Yeah.
Okay. So do you think if we train on an arbitrary corpus, do you think this train we can still observe such curves?
Yeah, I think so.
Now
Um,
we do not need train on long sequence data set. Yes, or no?
yes, you can definitely mix. I think you can mix short and long sequences. Then it should probably work. It's just my guess. Yeah.
For your guess, you're saying like we can, as long the training sequence length is like 16 K, and then
Mhm.
no matter the training corpus it is, maybe we can just train on Slim Pajama, on Fan Web EDU, stuff like that. As long the training sequence length is like large enough, and we should observe a similar tendency of your plotted curve.
My guess would be yes, but it depends on the ratio of actual long sequences in the data set. So I don't know what's the ratio. It's probably pretty low. So I cannot guarantee that. Yeah.
Okay, so previously you said for evaluation, we must be using some non-context data. This is for extrapolation or for like in
Mhm.
domain length, like smaller than training length, or like is extrapolation.
It's mainly within a training context then, but yeah, for extrapolation, you certainly if you want to see this kind of trend, of course, for example, here it's really going down. So if you want to see this, of course you are going to need long sequences.
Yeah, okay.
Mhm.
And then, can you go back to the slides where you have the comparison of like many R models curve with the forks and the transformers per position loss function? Oh yeah. So can we think I think for this kind of like R model, their loss become plateaued after like 4K sequences. Do you think like the effective contextness for this modern R are like 4K?
That depends on your definition of effective contact length. So as you can see, even though it starts to flatten after 4K, it's still decreasing. It's just not as quickly as the transformer. So it's
Uh,
not that's not a like a particular. So it's a gradual process.
what do you think is the main reason for this phenomenon? Do you think it's because the recurrent hidden state size of these arms are still too small, and if we can find some way to increase the state size, we can have better plot, even closer than those of like forks and transformers.
Yes, that's exactly what I think. So you just need to increase the state size in some way. And also what I observe in my experiment, and many people perhaps already know this, is that if you train larger recurrent sequence models, you'll get better protocol loss. So and there are probably two reasons for that. One is the larger models have a larger state size. And second is the larger models have a stronger modeling capabilities. Maybe it's is better at compression, so you can utilize its fixed state size better. So it has a better orthogonal loss curve. Yeah.
Yeah, what if like for a recurrent neural network, when the recurrent hidden state size is like 16K sequenceless KV cache size, do you think like in this scenario like recurrent models would have like a similar or even better per token loss than the transformer counterparts?
I think it's definitely going to be better. Yeah.
Yeah, so you think like
Yeah.
fix the state size. So imagine the KV cache size as the state size. So when they are comparable to each other, you think the recurrent model should always be better.
Yes. Especially because nowadays we have a delta net, which is arguably more expressive than I guess softmax attention in some aspects. And those for example TTT and Titans, they can be seen as implementing some kind of a delta rule in there. So that should be better than transformers if they have a similar state size. Yeah.
Okay, so you think the state size is what matter? It's not like the softmax operator.
Softmax operator can, well,
It's
it
like
depends on your definition of a state size. There needs to be a precise mathematical definition, right? Because even if you can argue that linear attention also has an infinite state size if you use the parallel view of linear attention, but that's just not the case. I guess that there needs to be some mathematical definition of state size, like what's the maybe some information theory like definition for that. Yeah.
yeah, interesting. So are there any other questions? Okay, seems that we don't have a further question, so maybe we should end
Yeah.
it here. And thank you again for your amazing presentation.
Yeah. Thank you for having me. Yeah.
Bye.
All right.